Hello, and welcome to this Isabellenhuette USA webinar. My name is Matthew, and I will be your Global Spec moderator, and I want to review a few housekeeping items with you before we begin. Please take a moment to familiarize yourself with the operation of the user interface for today's webinar. The windows with the heading Presentation are the primary windows for today's event. On the right side of the screen is the Speaker Bio window, with background information on today's presenter. On the bottom left of the screen is the Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will be placed in the queue to address when we get to the Q&A session. At the bottom of your screen, you will see additional buttons to enhance your webinar experience. To see what a particular button does, just place your mouse pointer over it and a tooltip will appear with a description of the button's function. And now, I would like to introduce today's presenter. With us today, we have Matthias Hilpert, the Sales Director for Precision Measurement, coming to us from Isabellenhuette. To read more about Matthias, please look at the Speaker Bio window right next to the main presentation window. And Matthias, welcome to today's event. And with that, I will pass things along to you to get started.
Hello and welcome to this webinar about BDU Smart Sensing, presented by Isabellenhuette and Global Spec. My name is Matthias Hilpert, and I'm looking forward to dive deeper with you into the smart sensing topics in battery disconnect units. First, we'll talk a little bit about Isabellenhuette as a company, especially we're going to look at Isabellenhuette's value chain, what we call the value chain. Second, we'll directly dive into the topic. We'll talk about the definition of a BDU, what actually is meant by the term BDU, leading us to the third chapter, which is about different BDU designs and the role of smart sensing. And then we'll directly go into the right solution for your BDU design, especially with regards to high current sensing solutions. And lastly, we'll have a little outlook into future trends in BDU designs. Isabellenhuette, as one of the oldest companies in Europe, prides itself for having a very deep vertical integration of products and services. Having started off as a copper smelter in the medieval times in the mid-1500s, Isabellenhuette officially founded its Precision Alloys business unit in 1952, and until this day is still producing its own precision alloys. Later on, we decided to manufacture our own shunt resistors made out of our precision alloys. This business unit, which is the largest business unit today, was officially founded in 1987. In the early 2000s, we took our shunt resistors and integrated them higher into precision measurement modules. This youngest business unit is in existence since 2008. A couple of important milestones in the long Isabellenhuette history. In 1889, manganese was invented, an alloy that guarantees long-term stability with values in the parts per million range. In 1987, we started with our isoplan resistors, manufactured from etched, homogeneous precision resistor alloys such as manganese or saarinen. In 1992, we started with our isoweld resistors, which are made of composite material, copper, and our resistor alloys. In 2016, the IVT series was launched, a shunt-based high-precision current measurement system designed for DC applications. And lastly, in 2019, we launched our first DC energy meter called IEM. With regards to the automotive industry, our products are used all over the vehicle, be it in traditional internal combustion vehicles, in hybrids, or in all-electric vehicles. Our products are used in DC-DC converters, power electronics, motor control units, transmission control, BMS systems, charging sockets, onboard chargers, and charging stations. Now, let's talk a little bit more about the definition of a battery disconnect unit. A battery disconnect unit, or short BDU, sometimes also referred to as battery distribution unit or power distribution unit, in short PDU, always describes the unit that is able to disconnect the high voltage battery from other subsystems in case of an accident or when the vehicle is powered down. This unit also distributes the power from the high voltage battery to subsystems like the vehicle drive inverter, the high voltage heating and cooling system of the vehicle, as well as the DC-DC converter for the low voltage battery system. It also handles incoming charging current in case the vehicle is charged. The main components found in a BDU are the precise current measurement sensor, which reports to the battery management unit and contributes to the state of charge and state of health calculations, as well as of the determination of the battery gauge in the vehicle. There's typically some high voltage measurement units as well to determine the total battery voltage, as well as check on relays, state of relays or state of fuses. The total battery voltage is typically used to calculate the total power flow in and out of the battery. There's sometimes an isolation monitoring device, even though this is sometimes also integrated into the battery management system directly. And there's a whole bunch of contactors, typically to separate the link side of the high voltage circuit from the battery side. And these are typically found on the plus side and on the minus side of the battery, as well as in the pre-charge circuit. Lastly, there's typically a redundant current measurement module, which is frequently a fast measuring analog device. This is typically done in order to achieve higher functional safety ratings in the battery system. There's also at least one fuse, which is mostly a pyro fuse, but sometimes also a mechanical fuse, which can disconnect the battery from all the subsystems in case of an accident. Now that we know what a BDU is and we learned about the definition of a BDU, let's talk a little bit more about different BDU designs and the role of smart sensing. So we see 4 different types of BDU layouts with regards to the sensing functionality and also with regards to the type of communication between the BDU and the BMU, so the battery management unit or battery management system, BMS. The first type we see holds what we call a smart multi-sensor. So it holds a lot of the sensing functionality in the BDU. It would have an analog front end itself, so it would do like the AD conversion in the module and send a digital signal to the battery management system. The second type would still hold a digital current and or voltage sensor. So the AD conversion is there still done in the sensing module and the digital signal is sent to the BMS, while other functions would communicate analog signals to the BMS. In the third layout, we would see an analog shunt sensor. An analog signal would be sent to the BMS, and the analog front end in the BMS would convert that into a digital signal, as well as the other input signals from the BDU would be analog. And the fourth type is basically a subversion of the third type. So the difference here is that the analog shunt sensor would report to a separate BDU controller that itself would report digitally to the BMS system. So there would be a dedicated BDU controller that would have the analog front end for a shunt sensor and other sensing inputs from the battery disconnect unit. Now let's talk a little bit more about the individual designs that we looked at on the slide before. The first one here being the BDU design with a so-called smart multi-sensor. So in that case, really all the main sensing functions in the BDU would be integrated into one smart sensing device that would have a digital interface with the BMS. So the BMS would basically save the analog front end. So the complete analog front end would be in the BDU. This smart multi-sensor would include several sensing functions like high accuracy current sensing, internal temperature sensing, high voltage taps, so high voltage sensing functionality with multiple channels, to control the battery voltage, the state of contactors, the state of fuse, and so on. It would even include, or it could even include, an isolation monitoring device. It would have an ASA rating on all the main functions like the current sensing, the voltage sensing, and the isolation monitoring device. It could include a redundant analog channel for, depending on what ASA rating is necessary. Also an analog overcurrent detection for fuse and relay control with the ASA rating that's necessary, or even a whole fuse integrated within the smart sensor. So a complete package basically that has all the main functions of the BDU. So a design like that would typically, an OEM would typically buy a finished battery system from a battery system supplier. So it would, the OEM would obtain the complete package. As I said, the BMS would control all the BDU components through a digital interface, so no analog front end required in the BMS. And the smart sensor is really, the smart multi-sensor, I should say, is really the main component of the BDU in that case. And obviously, in this case, the software design lead would be at the battery system supplier as they deliver the complete system to the OEM. So the second type would be a BMS with a digital current voltage sensor in the BDU. So this is a little bit less highly integrated than the first type we looked at. So basically here we would still have a digital current and or voltage sensor in the BDU that has an analog front end and would do the AD conversion in the module and communicate digitally to the BMS. The BMS itself would have an analog front end as well, as it would take several inputs from the BDU, analog inputs from the BDU like voltage taps, contactors, and pyrofuse. The digital sensor that would be used in such a case would still provide the high accuracy current sensing, internal temperature sensing, optionally the high voltage channels for battery voltage and relay control and other functions. It could still have an ASA rating on the current and the voltage sensing if applied to help achieve a higher rating on system level, but typically there would be a secondary analog sensing channel there to get to a high ASA rating on system level. There could even be like an analog overcurrent detection for fuse control integrated in such a module to basically bypass the BMS and have the advantage to actuate the fuse even faster than it's possible if this has to go through the BMS first. In that case, the OEM would typically select critical BDU components, among them the smart sensor, directly, and would have basically do a directed buy for these components with their selected tier 1 BDU supplier. As I said, the BMS would have more analog interfaces. Typically, the smart sensor would here be the only digital interface coming from the BDU. And as in that case, the OEM is not buying a complete package from a battery system supplier typically. The design lead software design lead would partly be at the OEM, as the OEM selects components, depending a little bit on the fact if the OEM is actually designing the BMS themselves or if they have like an external company do the BMS design for them. In this third type of BDU design that we see, we would basically look at a completely analog BDU. So the shunt sensor and all the other sensing functions or signals from the BDU would be analog, means also that the analog front end would be completely in the BMS system. In that case, really the sensing function, the current sensing function here is reduced to a main current sensor, which is typically shunt-based and analog. So it would have an analog output signal. The current sensor in that case wouldn't come with any functional safety rating, so it would support to achieve an ASA rating on system level together with a secondary analog channel typically, which would also be designed into the BDU. This current sensor could also be designed as a dual channel solution, which means it could have either a shunt and a Hall channel in one module or even a dual shunt solution that would basically have two different sensing paths, independent sensing paths in one module that would also allow for a higher ASA rating on system level with those two analog signals coming from one module. So the analog front end and the microcontroller in that case are located within the BMS. So there's no component in the BDU that has an actual microcontroller. The advantage here, or one advantage here, is that BMS design of that nature would allow multi-platform compatibility because you can easily use it on different platforms. It only has analog inputs. So you don't have to worry about rolling this out to a different vehicle platform, for instance. Software design lead would here be at the OEM, or again, in case the OEM has selected an external BMS supplier, would be at that BMS supplier. Another advantage here would be the reduction of digital subsystems. So there's a cost reduction because there's no component in the BDU that actually uses a microprocessor. And obviously all the computing power in that case is centralized within the battery management system. The final and fourth type of BDU design that we see is basically a subtype of the third type that we just looked at. So again, the BDU here has only analog signal outputs, but in that case they don't go to the BMS alone, but they go to a dedicated BDU controller that has an analog front end itself and works signals from the shunt sensors or Hall sensors, the fuse, voltage taps, in some cases the contactors, but sometimes they would report directly to the BMS too. This BDU controller would in some cases also take the cell voltages directly and process these and then report these to the BMS afterwards. So with regards to the sensor, to the shunt sensor, it's very similar to the type 3 that we looked at before. So there would be one analog main current sensor, which is typically a shunt with the analog interface to the BDU controller. And again, this shunt sensor would support with functional safety rating on system level. And again, there would typically be a separate secondary current sensing module here that could also be included again into one, but that would be exactly the same as for type 3. The BDU controller here would really control all main BDU components, which is the main difference. So the analog front end and the microcontroller are now located within the BDU controller, or there's a second analog front end microcontroller in the BDU controller on top of the actual BMS controller. So also that would facilitate multi-platform compatibility here. The software design lead in that case again would be at the OEM or a dedicated BMS supplier, or even the like BDU controller supplier that the OEM selected. I want to add here that these are the four main designs that we as a smart sensor and shunt manufacturer see in the markets for BDUs. This doesn't have any claim to completeness though. So there's a high likelihood that there's other designs, or I'm pretty sure there's probably other BDU designs out there, but these are really the four main types that we run into as a manufacturer of one of the main components of the battery disconnect unit. Now that we had a detailed look at different BDU designs with regards to smart sensing and current sensing, let's take a look at actual products that would fit these four BDU designs with regards to current sensors and or smart sensors. For our type 1 BDU, where we have the smart multi-sensor that has a digital interface to the BMS system and provides the whole analog front end for the BDU, we recommend our IVT3 Pro module. The IVT3 Pro module was fully developed according to the ISO 26262 functional safety standard, and it, as a feature highlights, it actually has a high current sensing channel that has a plus minus 1000 amp range and 0.4% accuracy, and it is ASIL-C rated. Another feature highlight is definitely the 3 or 6 high voltage channels, which are come with an ASIL-B rating. So these voltage channels can be used A for the battery voltage, which also enables energy counting functionality with this product, and B to monitor several relays on link and pack side and plus and minus side, relays in the pre-charge circuit and fuses. And then we have the active isolation monitoring device, which is also ASIL-B rated. The difference here between an active isolation monitoring device and a passive isolation monitoring device is that with this product, you can monitor a non-energized bus. So the product will send voltage pulses through the bus and determine if the isolation is intact. And you get up to 5 different isolation readings. You get total isolation reading, you get pack and link isolation reading in case the contactors are open, or a plus and minus isolation reading in case the contactors are closed. Another feature highlight is an ASIL-D rated overcurrent detection for fuse control. This is currently under development and is a highlight that we want to add in the future, which actually enables the safety goal overcurrent detection for this product. Further features are temperature sensing, an energy counter, as mentioned before, for the primary current sensing channel, and the voltage channel that monitors the whole battery voltage, optional CAN termination, an independent analog output current sensing channel to basically supplement a separate current sensing module, and sleep mode. For our type 2 BDU, we would recommend our IVT3 base and IVTS modules. The highlights here are also the high accuracy, high current primary and shunt-based current sensing channel with a range between 100 amps and 2500 amps nominal range in case of IVTS. There we offer several current sensing ranges and a total range of 1000 amps for IVT3 base with total accuracy of 0.4%, and IVT3 base, just as IVT3 Pro, was developed according to ISO 26262 and hence has an ASIL C rating on the current sensing. IVTS is ASIL QM rated. IVTS also offers up to 3 voltage channels optionally. I should mention that IVT3 Pro obviously has the voltage channel option and can be ordered also without the isolation monitoring device if that's not required. Also for IVT3 base, we have this ASIL D rated overcurrent detection for fuse control under development to enable this safety goal for the future. Other features here are again temperature sensing, an energy counter in case voltage sensing is equipped, CAN termination, and sleep mode. Lastly, for our type 3 and 4 BDUs that have a complete analog BDU basically, and the analog front end is completely situated either in the BMS system or in the BDU controller, we recommend our BSX or IAS series. The feature highlights here is that our analog BSX and IAS series provide up to 3 analog current readings, 3 independent analog current readings from independent sensing points, which also enables ASIL D capability on system level, and up to 2 independent temperature readings from independent NTCs. Here, also under development, is a configurable ASIL D capable current sensing channel. This would be for IAS, as IAS in comparison to the BSX series is an active product, so it's an active power supply, while BSX is a passive product, so it's not powered by itself. Further features here are measured resistance value that can be printed on the data matrix code, and also even TCR value and NTC data that can be printed on the data matrix code for the BSX series, which enables the customer to get to a higher accuracy because it enables the customer to do active temperature compensation in their battery management system. Now that we've looked into different BDU designs and we've analyzed the products that are available today for the different layouts of BDUs, let's take a look into future trends in BDU design in this next chapter. For the future of BDU designs, we see a couple of major trends that I would like to discuss here at the end of our today's webinar. Obviously, the trends that influence the BDU design are a little bit linked to trends that influence the whole electrification and EV business in general. So everything is influenced by the constant technological advancements that we see in this market, talking about new battery systems like solid-state batteries and so forth. Also, a big role obviously will play regulatory changes. The regulations worldwide are still developing in this field at the moment, especially also in the field of charging, going from the state-of-the-art DC fast charging to megawatt charging will bring changes. And not last not least, also the demand for electric vehicles. So this is growing strong at the moment. It's ever changing too. So all these factors obviously influence also on the designs of future BDUs with regards to smart sensing. Talking about different trends, so one major trend that we see is the call for improved safety for BDU systems. So we see a clear trend from an ASIL D requirement at the system level to an ASIL D requirement on component level. This also, with regards to the safety goal, we see that there's a trend towards an ASIL rating on overcurrent detection, especially with regards to the kind of level that needs to be achieved. So for overcurrent detection, we see for the future that most customers call out an ASIL D requirement. And if you think about it, that makes sense because the overcurrent detection is very critical in the vehicle, because if an overcurrent detection is not reliable, in case of an accident, this can have a high impact. The overcurrent detection will typically trigger a fuse, a mechanical fuse, or in most cases a pyro fuse, and that will disconnect the battery in case of an isolation fault or an accident. So if this system doesn't work properly, it directly impacts human safety. The second trend that we see is towards modularity and scalability. I tried to touch on that a little bit on the slides before with regards to the BDU designs, where I showed like the BDU type 3 and 4 that had like more analog interfaces. So a goal here of the OEMs is definitely to be able to roll out designs to different vehicle types, battery types and sizes, and power levels. And that can be achieved by basically making the interfaces homogeneous and easier to roll out. And obviously, if you think about it, those more integrated assemblies, they're easier to roll out, can achieve cost savings. The third trend that we see is definitely towards higher power density in the battery disconnect unit. So obviously there's the trend for megawatt charging out there that is evolving fast. With that, we are confronted with very high currents in the battery disconnect unit. So all the modules in the battery disconnect unit means the sensors, the relays, the fuses, everything has to deal with higher currents. So what does that mean? You have a lot of resistances, little resistances in the BDU. There's joint resistances, so where the fuses, the relays, the current sensors are mounted onto the bus bar. There's a bus bar joint, and there's typically some joint resistance. And this resistance is small, it's typically in the micro ohm range. But when we're talking about currents of 1,000 amps plus, even resistances in the micro ohm range produce a significant voltage drop, and that means heat at the end. So there's that. Then there's the internal resistances of the BDU components. So a shunt current sensor obviously has an internal resistance because it's a low ohmic resistor. And even relays do have an internal resistance. And all these resistances produce heat. So we definitely see the need for enhanced temperature management in the BDUs in the future. Also, obviously, all the modules in the BDU will have to have a higher nominal current range to basically comply with these new requirements. Lastly, we see the trend towards bidirectional charging, which can also influence on the BDU design and the BDU components design. With bidirectional charging, the current flow to the vehicles becomes bidirectional. So not only is the vehicle being charged, but the vehicle is capable to give electricity back to the grid or to home energy storage systems. And if we're talking about charging, we're typically always talking about higher constant current loads. Because if a vehicle is driving, there's typically like this short high current load during acceleration, and then it's mostly like coasting and like lower current. So the current profile is not as demanding with regards to the current load. While when we talk about charging or even like discharging or bidirectional charging, the current load is typically higher for a longer period of time. So there also we see the need for enhanced temperature management. Another factor here is that we have to talk about grid integration and possibly even communication with a controller on grid side. And depending on how high the integration is of the modules used in the BDU, means like the smart sensing module, this can affect the smart sensing module as well. And as the grids are very different worldwide with different standards and different frequencies and so on, modularity again is a topic here to be compatible with different grid standards all over the planet. So these are the 4 trends that we see. Again, there's so much going on in the field of electric vehicles. It's a very volatile market and there's so many influence factors. So I'm sure there's some other potential developments possible. But anyways, this brings us to the end of today's webinar. Thanks for joining. Thanks for listening. My name is Matthias Hilpert, and now we'll continue with the live Q&A session. Thank you.
Thank you so much for that great presentation. And now we're going to be moving into the Q&A session. We already have some great questions in the queue, so we're going to get to those in a moment. To the audience, if you have any questions or comments, we would love to hear from you. You can add that information to the Q&A box on your screen and click Submit. Now, we're going to try to answer everyone's questions here today. However, if we don't get to your question for whatever reason, we will reach out to you after the webinar is over. So please send us your questions. Okay, let's see what our first question is. Wow, a lot of great questions in here. Okay, here we go. Here's our first question from the audience. Can you give me an example of how smart sensing improved a BDU's performance or value? Matthias?
Thanks, Matt. That's a great question. So yeah, there's definitely a couple of advantages if you use a smart sensor over an analog sensor in a BDU. For one, the AD conversion is done right in the module. So that means you're definitely less prone to have any magnetic interference in the signal. And also you get a high accuracy output as the calibration is done right in the module. So you don't need to worry about any calibration in your microprocessor. Also, there's multiple functions that you can have in the smart sensor, like voltage sensing, temperature sensing, and even the IMD feature, as we saw during the presentation. So those are all like features that are included in this one smart sensor, which is also, I think, from my point of view, an advantage. On the other hand, I want to mention an analog sensor actually saves you some costs, so you don't have any additional microprocessor.
Excellent. Thank you for that. Okay, moving on to our next question from the audience. Where do you think the optimal location in BDU bus for the Type 1 multi-sensor so it can provide the best reading for voltage, current, and temperature of the BDU?
Yeah, thank you for that question. That's actually a good one too. So our smart sensor is actually designed to be applied both either on the positive leg or the negative leg of the battery. So it's bidirectional. So it will give you good readings, no matter if it's on the plus side or the minus side of the bus. Important is just that you basically use the signal inputs accordingly. So you would have to put like for a correct energy reading, you would have to obviously put like the first voltage tap on the opposite side of the battery. So it actually gives you the voltage input off the whole battery pack for the energy counter. And but yeah, I mean, our smart sensors are really bidirectional. They can be applied on the positive flag or negative flag of the battery. Typically, they would sit like right before the relay of either the negative or the positive leg on pack side, so not on link side, on pack side.
Very good. Thank you. Thank you for that question. Please keep sending them in. And to the audience, while you're thinking of your questions, I just want to point out on your screen, along the bottom, there's a series of buttons. We have a contact form that you can use to reach out to the Isabellenhuette team, and we do encourage you to do that. If you have any questions, would like to continue the conversation, or just want to chat about the industry, we'd love to hear from you. You could reach out anytime. Okay, back to our questions. And our next question is, why is the Hall sensor still shown in the BDU Type 1 and 2? Wouldn't the IVT3 ASIL C rated shunt allow to remove the Hall sensor?
Yeah, that's a very good question, and whoever asked the question is absolutely right about this. So the IVT3 with an ASIL-C rated current sensing, and especially if it's equipped with the supplementary analog channel, removes the need for a separate analog sensor. However, that is if your system requirement is ASIL-C, right? If you need to get to an ASIL-D requirement on system level, then you could use the ASIL-C rated IVT3 current sensing plus the whatever the internal analog channel or the external Hall sensor or whatever is applied to achieve this ASIL-D level on ASIL-D rating on system level.
Excellent, thank you, and that was a great question. Okay, moving along to our next question. Does BSX also have a sleep mode?
Yeah, thanks for the question. So the BSX line is an analog sensing product. So it doesn't have any power supply. It doesn't have any microprocessor and no CAN communication either. So it's an analog output signal. So that's why it doesn't have a sleep mode. However, our IVT line, the IVT3 line has a sleep mode that can be configured over CAN. It even has the ability to wake up by a dedicated CAN message or just CAN traffic.
Oh, excellent. Thank you. Okay, to the audience, we are in the Q&A session. We have our experts from Isabellenhuette online and ready to answer you. So please send us your questions. And I had a few thank yous come into the queue and also some requests about whether or not this webinar will be available in the future. So first of all thank yous I just want to pass along to Matthias and the Isabellenhuette team. And also for the entire audience, this entire webinar, including the Q&A session that we're in right now, will be available as a replay on the Global Spec site for the next 90 days. And you could use the same link you used today to access the replay. So we do encourage you to come back and watch this again. Okay, now for our next question from the audience. What technique is used by the isolation monitoring feature?
Yeah, thanks, Matt, for that question. So within our IVT3 Pro, we use an active isolation monitor. So as I explained during the presentation, the difference between an active and a passive isolation monitor is that with an active isolation monitor, you can measure if the isolation is intact when the bus is not energized, means when your relays are open. And this works in a way that the module will actually send a voltage pulse through the bus and determine if the isolation is intact. And it has like these 6 voltage sensing channels that are actually used for the IMD functionality, so for the isolation monitoring functionality as well.
Oh, that's great. Thank you. Okay, moving on to our next question from the audience. Do the products presented include a microcontroller or another type of controller and software?
Yeah, thanks for the question. So The answer is partly yes, right? So our active products like the IVT3 line and the IVTS line do have microprocessors because these products actually have the analog front end in the module. So they do the AD conversion, they do active temperature compensation, means like they do have NTCs that actively sense the temperature and basically always determine where on the TC curve of the resistive alloy the module is and actively compensate for that temperature error. And these calculations are done by the microprocessor that is used in these modules, plus the control of other supplementary functions like voltage sensing and so on. But our analog sensing modules, and this starts with our bare shunts, but also our BSX line and our new IAS line. These are new products. So the IS line is a new product, but these products actually don't have a microprocessor on them. So these are analog products, means they basically sense the voltage drop over the shunt. They determine the temperature too in some cases, in case of the BSX line, because they have NTCs on board, but the output is completely analog. So they basically just take this voltage drop from the shunt and give this out through a connector as really like this a couple of milliamp voltage drop that you get over this low ohmic resistor.
Thank you for that. And thank you for that question. I also want to take a moment just to thank all the audience members for sending in so many great questions so far. We really do appreciate it. Okay, here's our next question from the audience. How does the derated overcurrent protection for the fuse work? Is this a fuse internal to the IVT, or would this be to control an active fuse?
Yeah, thanks for that question. This overcurrent, so the overcurrent detection that we're working on, which is the new feature that's still under development, works in a way that we would use an internal analog. So it would be a separate channel from the CAN channel, the CAN interface channel of IVT, our active product. So an analog output channel that is basically used to trigger a fuse, right? So you would basically have the advantage that you would send this analog fuse trigger, this overcurrent detection. So it's an analog sensing channel within IVT plus an overcurrent detection. So this analog output signal would actuate only if it surpasses a certain configurable overcurrent threshold and fire the fuse. And the advantage here is that you would go around the battery management unit. So you would basically have this analog signal come directly from the analog current output of our sensing module. So it's not like an additional fuse or anything. So it's really just like a fuse trigger of a certain fuse. You know, it could be a pyro fuse or a mechanical fuse or whatever fuse you use. So it would be compatible with, you know, pyro fuses and other fuses on the market.
Excellent. Thank you for that. To the audience, we are still in the Q&A. You could send us your questions. We have a few more in the queue we're going to get to in a moment. But if you have any last questions or comments, please send them in. You could type that in the Q&A box and click submit. And as mentioned, if we don't get to your question, for whatever reason, we will reach out after the webinar is over. So please send in your questions. Okay. And here is our next question from the audience. How much space can be saved by choosing a smart sensor?
Yeah, thanks for that question. So, you know, you don't necessarily save like space in the BDU with a smart sensor. So it's really that you save some circuitry in the battery management unit, because you really like replace, you know, like part of the circuitry that you would have for all these smart functions in the BDU. So it's really more, you know, that voltage sensing channels or voltage sensors and everything would be located a little bit differently. So yeah, I mean, you would maybe save some space for a more compact packaging because you know, if you would imagine, like if you look at IVT3 Pro with like the 6 voltage channels, you know, if you would use like individual like voltage sensors for these, they would probably also take up some more space in the BDU. But it's really, you know, the main thing is like more like a relocation of these functions from the BMU into the BDU. And if you go like for like a, you know, the type 1 BDU design, you would really save the analog front end in the BMU because all the analog functions would be in the smart sensing module.
Very good. Great question. Okay, I see a lot of questions still coming in. We really do appreciate it, audience. Please keep sending them in. Again, if we don't get to it, we will reach out later. Okay, and here's our next question. At what point in the design process should we be looking at what kind of sensors we use in our BDU?
Yeah, that's a good question too. Thanks for that. So this decision should be made early on in the design process. I mean, as we've seen during the presentation before, you know, deciding what type of sensor you use really affects on all the interfaces, you know, to your battery management unit, and pretty much defines like what kind of or what type of BDU layout you're going for and pursuing.
Absolutely. Okay, let's see what's left. Okay, here's our next question. What is the advantage of having a fuse trigger integrated in a smart sensor versus in the BMS?
Yeah, that relates a little bit to the question that we had before. So the advantage here again is that you would basically trigger the fuse directly through the sensing module. So you would basically go around the BMU. That would shorten reaction times. And that's basically an advantage because it's safety relevant. So, you know, you would really like have this direct connection from the analog sensor. The only intelligence there would be the configurable overcurrent threshold, but it would be a direct connection between the analog sensor and the fuse. And this would be you know, typically ASIL D-rated, so that's also what we're aiming for our product.
Excellent, thank you for that. Okay, moving along to our next question. When will your ASIL C rated smart sensor be available for purchase?
So our IVT3 base sensor, that's the one that has like the current sensing functionality, ASIL C rated, is in mass production as we speak. I also want to mention here that it has received a certification from an independent institute, namely the TÜV Rheinland, and as such is the first current sensor of the on the market that has been rated by an independent institute. And then we also do have our IVT3 Pro, which has ASIL C-rated current sensing and ASIL B-rated voltage sensing, plus the isolation monitor, which is also ASIL B-rated. And that is currently available in B-sample stage and slated to go into production by Q1 25.
Excellent. And I also want to take this opportunity to again mention on your screen, there's a button to contact the Isabellenhuette team. So if you do have any further questions about purchasing their items or discussing anything in detail, we encourage you to follow up there and reach out. Okay, looks like we have time for a couple more questions, so we're going to get to that in a moment. But to the audience, now would probably be your last opportunity to send in any questions or comments, so please go ahead and do that now. And as mentioned, if we didn't get to your question, you can expect us to reach out to you after the webinar, so we will get to you. And we do appreciate you being here with us today and also sending us your questions. Okay, let's see what our next, okay, great. Here's our next question. Does each of the IVT voltage sensing provide measurements relative to chassis/low voltage, or would it be relative to the shunt, battery plus or battery, plus or minus battery?
Yeah, thanks,
So,
Matt, for that question. That's a good valid one. So the IVT voltage sensing channels all reference to shunt ground, so means like the negative side of the shunt module. This is marked on our sensing modules by a little minus that's stamped into the housing, and also the chamfered edge of the shunt is the minus side of the shunt. I want to mention here that, again, it doesn't matter if the module is installed on the positive or negative leg of the battery. It's bidirectional. It can measure bidirectional. You can even swap the current sensing sign in the software. If you want you want to swap the sign, have a positive or negative reading. But the voltage sensing channels are all referenced to shunt ground, so to the high side. So they're not referenced to the chassis or to the low side. The IMD, so the isolation monitoring device for IVT3 Pro, obviously has a reference to chassis because it needs it, right, to determine the isolation to chassis. But the voltage channels itself are all referenced to shunt ground.
excellent. Thank you for that. And thank you for that question. That was great. Okay, looks like we have time for about 2 more, so we're going to get to that now. Here's our next question. Do you see the need for ASIL D rating on component level in the future?
Yeah, thank you. I tried to touch on that a little bit in the presentation too. So there's definitely a trend for a higher safety rating on component level in the future. The reason for that is simply to make the life of the OEMs easier, basically. So if components have a higher ASIL rating already, that eliminates the need for redundant components. And saves cost, and it also facilitates to achieve higher ASIL ratings on system level, or achieve the ASIL D rating on system level. And that's basically the main reason.
Excellent. Okay, to the audience, we have one last question we have time for. We'll get to in a moment. But again, if we didn't get to your questions, we will reach out after the webinar is over. Seems like a good ending question, and here it is. What is the trend for safety goals for current sensors in the future?
Yeah, that's indeed a good last question here. So, as I mentioned, so we see a trend towards safety goals and overcurrent detection for current sensors. And if you think about it, this really makes sense, because the overcurrent detection directly influences on the safety in the vehicle, because that's typically what's used to either open relays or fire the fuse. So in case of an isolation fault or in case of an accident, there's an overcurrent, it's a very relevant safety measure. And that's also what we, at least as a smart sensor and shunt supplier, see in the market. So while there was a lot of calls for ASIL rating, functional safety rating on the current sensing itself, in the future, it seems like the market is moving towards this safety goal of overcurrent detection. Excellent.
Thank you for that. And that was our last question, so we are gonna wrap things up right there. So once again, Matthias, thank you so much for the great presentation and also answering some questions from our audience today. And of course, we'd like to thank our audience members for being part of this webinar event. You will be receiving an email from us with a link to the on-demand version of this presentation. So as mentioned, you can come back and watch this again or share it with your colleagues. And lastly, if you could, please take a moment to complete a survey which will appear on your screen at the end of this live webinar. For on-demand viewers, you will find the survey located along the bottom of your attendee console in the survey widget. Again, thank you for taking the time to attend this webinar event. Take care, and we will talk with you soon.